5, here we go. I'll start with questions. We're gonna stick with integration by parts today. We're not doing anything new. But that's not to say there won't be new stuff. But it's all going to be the same sort of technique. So, questions on problems I assigned for homework? Number 12. We did that in class? What? We did something. What did we do? We did X arc sign? No, we did this one. Yeah, so it's exactly the same, just take the pi out. Yes. 11. Arctan 4t dt. Okay, well, the thing that we really want to try and focus our attention on today is, I mean, we know we are going to use integration by parts because we're in that section, right? But really getting our head around our choice of u and our choice of dv, because those are the two things we have to choose in the beginning, right? We're going back to the formula. It was u v prime. This integral turns into uv minus v u prime. Right? That's our formula, where we have to choose something for u. The other thing we choose will be the derivative of v, and in the new integral, you have the derivative of u and the antiderivative of v prime. So in this integral that we're presented with, we need to try and choose a u and choose a dv. So any ideas here? Okay, so I don't have a whole lot of choices here, right? I mean, really, I have two things here. I have arctan 4t, and the other thing I have is a dt. Those are the only two things really present in my integrand. Now, why would I not choose u to be dt? Because then the derivative of that, again, would be like the derivative of the derivative, which would be like a second derivative, and that we will never do that, okay? Never, and we can say never, all right? We will never do that. So that really leaves the arctan 4t as my only candidate for u. Now I'm going to switch my notation. Instead of writing arctan, I'm going to write this version of it instead of using the arctan. And then that means that my dv must be what? dt. So when I look at this and I set this up, I'm subconsciously saying, am I going to be able to integrate this one up? So am I going to be able to take the antiderivative of dt? Yes, right? And am I going to be able to take the derivative of arctan? Yes, there's a formula for it. So I've chosen my u and my dv. So now I'll get a derivative here. The derivative of arctangent 4t, be careful here, is 1 over 1 plus 4t squared, which is 16t squared, right? But then times the derivative of what was inside by chain rule. So derivative of what's inside is 4. How about I put that 4 on top? Is that okay? Put the 4 up here instead of out here. And then what's still out here? dt, the differential, right? dt. All right, now when I integrate dv up to v, the antiderivative of dt is the same as the antiderivative of 1. The antiderivative of 1 should be the variable. The variable here for us is t. So this should just be t. So then we look, this is what the new integral is going to be, right? Our new integral is voodoo, vu prime, voodoo. And so just real quickly look at this. Is this something we're going to be able to handle? Well, what are we going to have? We're going to have 4 over this times this t. The t will come and join the 4, won't it, up top? So we'll have 4t on top. We'll have 1 plus 16t squared on the bottom. Right? Does everyone kind of see, before I write it all down, that we will be able to integrate that because the bottom, 1 plus 16t squared, if we call that u, do a basic substitution, the derivative of that would be what? What's the derivative? 32t. We have what? We would have a 4t, wouldn't we? So we'd be off by a constant. We want to try and get to that point where we're seeing all of this before we're doing it. It's like it saves you a lot of time and energy. So let's go. Let's rewrite the integral. This becomes ultraviolet t times arctan 4t minus integral voodoo. So I'll put 4t over 1 plus 16t squared dt. Did I get it all there? Everything accounted for? Okay. Now, could I pull that 4 right here out? Yes, I could. I could have. I just left it there. So now, focusing all my attention on just this integral, I'm going to go ahead and do that on the side. So I'm going to do some scratch work over here and figure out what that integral is. I'll do it in green. What is the integral? And I'll pull the 4 out over here. Of t over 1 plus 16t squared dt. I'm making a basic u substitution. U is equal to 1 plus 16t squared. The derivative of that is what? We said 32t dt, right? The 1 plus 16t squared right here is going to be replaced with what? U. So that's going to be u down there. T dt I have down here. I just have that 32. I need to get it out of there. So maybe multiply both sides by 1/32. And so I'll be able to replace that t dt right there. It's going to be replaced. So the yellow is going to become u. The blue is going to become 1/32 du. So my new integral is 4. What else can come out there? 1/32, and that'll reduce out to be 1/8, right? Integral, what's still in there? 1 over u du. And so the antiderivative of 1 over u is natural log of u. So I have 1/8 is my constant. Now I'm going to take the antiderivative, natural log. Do I need the absolute value here? Well, what's u going to be when I plug it back in? 1 plus 16, that's always positive, right? So I won't use it. So 1/8 natural log 1 plus 16t squared plus a constant. Questions? We're not done. I need to put it all together, but any questions on this part of it? So final answer, going back up here, t times arctangent 4t minus what we just got, right? Minus this integral was all this, came out to be this. So minus 1/8 natural log 1 plus 16t squared plus a constant of integration, box it up, and move on. Questions? Now, what made this one, I guess, relatively easy, I'm not saying it's easy like trying to insult anyone, but the fact that there really wasn't a whole lot to choose from when it came to U and DV. I mean, Now, you had to know, let's try integration by parts, but like I said, the section kind of tells us that. But anytime we see inverse trig functions by themselves, it's usually the standard technique is just let that be u and let dv be dt or whatever and go back. And that usually works for inverse trigs if they're by themselves. Okay, other questions on the homework? 15? Oh, 15, yeah, that was a bit of them. Okay. Okay, well, you know what? I'll address 15 later. But, okay, so any other questions? I'll get back to that. Okay, we'll have plenty of time, I think, to do more integrals because I only have 1, 2, 3, 4, maybe 5 integrals that I want to go through in my lecture today. So after I'm done with those, I'll just kind of like, we'll look at some problems in the book and see. But for those of you who actually sat down and did attempt this homework, I mean, what's your feeling on integration by parts? I mean, it's tricky if you guess it. Yeah. It can be, you can get lost with these pretty quick. And I've talked to a couple of students about this. Your first exam in this class, I think, is one of the hardest ones of the entire semester. And I've said this before, because it's all going to be techniques of integration, basically. And for each problem, it's not going to tell you what technique to use. So call it, technique recognition. Not only are you going to need to know how to apply the technique, you also need to know what technique to use. Right now, we only have, the power rule, the substitution, integration by parts. Next class, we start trig sub 1, and then next class after that is trig sub 2, and then after that is partial fraction decomposition. So you have various methods to apply, and kind of guessing the right one. You don't want it to be a true guess. You want it to be an educated guess, that you've done enough of these that you kind of, I've seen something like this before. So on the handout that I gave you for notes for this section, remember this? We had done A, B, and C. We had not done D. So part D, or integral D, is, I'm calling it pulling a rabbit out of a hat, integration by parts. If you go back and look at your notes, the first one we ever did was just, hey, this is how integration by parts works. Then we said, hey, look, this one, not so obvious, but integration by parts works. And then on part C, that's the last problem we did. That's where I showed you, sometimes you have to use integration by parts more than once to get to the answer. This one, not very natural, but it works. So I'm going to try and pull a rabbit out of a hat here. And I want to go back to those notes and start pointing something out here. When we did A, this first one ever, we chose our u to be x. Why did we choose our u to be x here? Because the derivative of it is 1. So in the new integral, the x vanished, right? It went away. And then this was our dv, and that we were okay with because we can integrate sine. So that's why when we did integration by parts, we chose it that way. In this one, our choice of u was this, not that, but was that arc sine part. Why? Yeah, we're not going to use dx as u. That was our only real choice, right? In the third one we did, we chose our t squared to be our u. Why? Because in the new integral, it went from t squared to 2t, right? And then we did integration by parts again, and that 2t went down to 1 or 2, right? So we tried to get the integration by parts to kill off one of them, right? And if it's a polynomial, like x or t squared, we know that if we do integration by parts enough, one of them will go away, right? But look at D. With D, if I choose u to be e to the 2x, and I choose v to be cosine x dx, what's going to happen in the new integral? What are we going to have in the new integral? The derivative of this, which is itself, right, times 2. And the antiderivative of cosine would be sine. So you'd still have e to the 2x in there, you still have a sine. So if I do integration by parts again, they're still gonna be there, right? This one's still gonna keep on circulating back and forth between sine and cosine, and the derivative of e to the x is still gonna be e to the x. So it might appear that you're not gonna get anywhere with this, right? But you can. And so let's just work it through and see what happens, all right? All right, so let's make a choice. I'm going to choose integration by parts here. I'm going to go ahead and choose my u to be e to the 2x. And I'm going to choose my dv to be the cosine x dx. You could have done it the other way. You could have let your u be cosine and dv be e to the x, because you know the derivative of cosine, you know the antiderivative of e to the 2x. So you could have done it that way, all right? The reason I chose to do it this way is just because I like the antiderivative of cosine more, right? The antiderivative of cosine should just be sine. So that's why I'm doing it. All right, what is the derivative of u? So what's the derivative of e to the 2x? 2e to the 2x, right? dx. So that's chain rule involved there. And then what's the antiderivative of cosine x? Sine x. Okay. Let's set up our new integral. I'm going to go ahead and put it up here. It's ultraviolet. So e to the 2x sine x minus the integral of v du. That new integral, how about that 2? Can I pull that 2 out front? Yeah. And then what's in the integrand if I pull the 2 out? E to the 2x sine x dx. And it appears by doing this that we haven't really gotten anywhere, right? I think we could all agree that this e to the 2x sine x dx is equally as bad as this. We've gained no ground, it appears. But I'm going to apply integration by parts again. I'm going to call u and dv again. Now, I will warn you on with something here. What if this time we said, let's let this be the sine x, be the u, and then the e to the 2x be the dv? Wouldn't that take you right back to where you were? I mean, well, I mean, wait a minute, hold on. That's not arc sine. That's sine. So the derivative would be cosine, right? And your integral would be 1/2 e to the 2x. And then when you put it together, what would happen basically is you would get things to cancel, and you would get this integral equals itself. What I'm trying to get at is if you get something like this, and you let the first time you did integration by parts, you said e to the 2x, and this one you said cosine, on your next integration by parts, keep it that way. Stick with e to the 2x and then whatever the trig function is. Because if you go back and switch them, you're going to wind up right where you came from. So I'm going to let u be e to the 2x. dv is going to be sine x dx. That okay? What's du? Again, 2e to the 2x dx. What's v? Negative cosine x, right? Antiderivative of sine is negative cosine. So this integral, and I'm talking just this integral right here. Keep track of that -2, right? That -2 is still in front. This integral becomes ultraviolet minus voodoo again, right? So watch, I'm going to rewrite the entire problem down here. All right, well, you know what I'm going to do? I'm going to try this. I don't know if I'm going to be able to squeeze room in here. Oh, that worked pretty good. I'm going to rewrite the entire thing, okay, the entire equation, and I'm going to replace this with the ultraviolet minus voodoo off this table. Okay? Integral e to the 2x cosine x dx equals e to the 2x sine x minus 2, and then in brackets, here comes my ultraviolet minus voodoo. So ultraviolet is what? Negative e to the 2x cosine x, right? That's these two multiplied. And then minus integral voodoo. But doesn't my voodoo have a negative there? Negative times a positive 2. But then I'm subtracting it, so it should become what? Plus 2. So is it all right if I put plus 2 there? Integral what? E to the 2x cosine x dx, close my bracket. Any questions? Where any of this came from? This whole bracket is that red thing, right? And now look at your new integral. What's your new integral? E to the 2x cosine x dx, which is the same thing we have over here, right? So you might be saying, oh, great, what's the point, right? We're back where we started. But check out what happens here. Rewriting the entire thing. Integral e to the 2x cosine x dx equals e to the 2x sine x. Now I'm going to distribute the 2 through. The negative 2, sorry. When I distribute negative 2 through, I get plus 2 e to the 2x cosine x. And then what? Minus 4 integral e to the 2x cosine x dx. That's just distributing the negative 2 through. Now check this out. I've carried this equation the whole time for a reason, because I want you to see that we have an equation here, right? The left side's equal to the right side. The integral on the left side appears on the right side also, doesn't it? Except this is how many of these integrals? How many integrals do I have here? What's the number sitting in front of this? A 1. How many of these do I have? Minus 4. So couldn't I just add 4 of these integrals to both sides of the equation? It's like if you have, x and negative 4x and you want to move all your x's to one side, you add it to both sides. That's exactly what I'm going to do here. I'm going to add 4 integrals of e to the 2x cosine x dx to both sides of the equation. Isn't that kind of clever? Now what will happen on the right side? They're gone, right? On the left side, how many integrals do you have now? 5 of them. And the 5 is just a constant out in front of the integral. But notice on the right side, what do you not have anymore? You don't have an integral. There's one more step. Get rid of this 5, right? Because we wanted to know what this integral was, right? Not what five of those integrals are. So how do we get rid of the 5 here? Divide everything by 5 on both sides of the equation. So we are at our answer. Our answer is integral e to the 2x cosine x dx equals 1/5 e to the 2x sine x plus 2/5 e to the 2x cosine x. Now, yeah, we need to make sure we say, hey, hold on. We use some kind of trickery here to make this happen. We know this is the antiderivative, but all antiderivatives should have a constant of integration. So we're just going to throw plus c out here. The thing that should tip you off to an integral that's going to behave this way is the cyclical nature of the derivative on these, okay? The two things you had there, e to the 2x, the derivative is e to the 2x, e to the 2x, e to the 2x, keeps doing that. The other one, cosine sine, cosine sine, cosine sine. So you know you're never going to get that to go away. So anytime you see that, you're going to start thinking, I'm going to need it to appear on the other side of the equation and bring it over. All right, that's it for that one. So the next example in my little, whoa, what's that? In my notes is integral e to the square root of x dx. And this is an example, I'm kind of giving it away already. This is an example where we want to make a basic substitution first before we try and integrate. So let me just get to it. Would you like to try integration by parts first without making a substitution? Sure, let's try it. Let's just see what would happen. What do you want your u to be? What do you want your dv to be? U is e to the x, because you really don't have a whole lot of options here, do you? E to the root x, dv is dx. What's the derivative of e to the x? Itself, right? Times the derivative, what's up there? What's the derivative of square root of x? 1 over 2 root x times dx. Agreed? What's the antiderivative of dx? X. So this is x. So this becomes ultraviolet minus voodoo, or integral voodoo. So integral voodoo. When I put those two together, what does the x on top of this root x become? Just square root of x, but on top, right? So I'm going to have a 1/2 will come out. I'll put that up here, 1/2. I'm going to have the e to the root x is still there, but now I'm going to have a root x there with it, dx. And you might argue that that looks maybe even a little more complicated than this one. Maybe? I don't know. What do you think? You could maybe try integration by parts again. Basic u substitution here, maybe? Right? So the point of this problem is that it'll work out a lot better if you make a substitution first before you do the integration by parts. All right? So this is all just to show you that this is going to lead you into maybe a 30, 45-minute problem. So I'm going to scrap this. I'm going to say, okay, let me reapproach this. Okay, let me just try something different. So I'm just going to go, don't know. E to the square root x dx. So I'm going to make a basic substitution. Now, the only reasonable substitution that I can make here would be like the root x, right? It wouldn't make a whole lot of sense to make it e to the square root of x, because that's basically what we did with integration by parts. We let this be u, the whole thing, right? And we don't want to ever let our basic substitution just be x. Now, I'm going to choose to use something other than u for my substitution because integration by parts is going to come. So I don't want to mix my u's up. So I'm going to use a different variable. How about t? Is t okay? All right, here it comes. Basic substitution. If you like, you can start putting BS. just because it's cool to be able to say this BS, basic substitution, right? Square root x. T is square root of x. How do we do basic substitution? Make the substitution, then derivative on both sides of that, right? Derivative of t is dt. Derivative of root x is 1 over 2 root x dx. Now, this is a little tricky, all right? That's why I'm showing you. What are we going to be able to replace square root of x with? With the t, right? With the t. So we got that covered. But I'm supposed to see something in its derivative. That's what we always said with substitution. Like, do I see something in its derivative? Well, the derivative of square root of x is 1 over 2 root x. That doesn't, it's not sitting here anywhere, right? It's not here? Correct? But, look, I just want to figure out what dx is so I can replace this dx. Normally, we just multiply both sides here or divide both sides by a number to get that dx by itself, right? But instead, I'm actually going to clear all this out. So I'm going to multiply both sides of this equation by 2 root x. When I do that, 2 root x dt equals dx. Agreed? Multiplying both sides here by 2 root x. What's the problem if I try and replace dx with 2 root x dt? What would be wrong with that? I have an x and a t still in my integral, right? I still have x's and t's mixed together. I need my integral to just have t's. Does anyone see what I can do with that root x, though? Yeah, I can replace it with t, because what is t? T is root x. So if I just come here and rewrite this, this is 2t dt. That's dx. The only reason this worked out so nice for me is because t was root x. If t wasn't root x, then I would have a major issue here. All right. Next. Can I rewrite now? I'm going to replace dx with 2t dt. I'm going to replace the square root of x with t. So this new integral becomes e to the, what? T. Dx is 2t, so I'm pulled the 2 out. Can I put the t in front of the e to the t? dt. That's my new integral. That's what my basic substitution got me, is that integral. Now, what about integration by parts on this? Yes, because if I let my u be what? T, then in the new integral it's gone. And if I let my dv be e to the t, in the new integral it's itself. So I'll just be integrating e to the t, which is straightforward. See that? Okay, so let's finish it off. I'm trying to do integral 2 times the integral t e to the t dt. I'm coming in with integration by parts. I'm choosing my u to be t, my dv to be e to the t dt. du is 1 dt, and then v is itself, e to the t. Here comes my new integral. It's 2 times, and I'm going to use brackets here, ultraviolet minus voodoo. Ultraviolet is t e to the t minus integral voodoo is e to the t dt. Am I moving too fast, or what's the deal here? You'll need to let me know. Am I moving too slow? Okay. Everyone responded to that. quickly. We going to be able to handle this integral right here? We don't need any technique for that, right? That's just basic, antiderivative e to the t is itself e to the t. So we have 2 bracket t e to the t minus e to the t plus a constant. I'll close my bracket here. Which gives me, I'm going to write it down here, 2t e to the t minus 2 e to the t plus 2c, but it's still just a constant, right? I don't know what c is, so 2 times c is still a constant, so it doesn't matter. You'll see this, like if you ever check your answers in the back of the book, like if you ever have to distribute a constant through to the constant you don't know, it'll always just leave it as a constant. And you'll be like, what happened to the 2? Well, it's still just a constant, right? Kind of. Yes and no. Yes and no. We're going to change kind of the whole meaning of everything later. But what we're going to do is we're going to actually have some sort of reason as to why we would ever want to find an antiderivative. It's going to have geometric implications. And we're going to have to find the antiderivative still, but we won't have to worry about the constant. That'll be when we do what are called definite integrals. These are indefinite integrals. Indefinite meaning we don't really know exactly the answer because we know it within a constant, so we're kind of not sure, indefinite about it. Definite is like we have an exact answer. All right, are we done? No, because you can't leave your answer in terms of t. The original problem was in terms of x. So we have to just replace t. T was square root of x, wasn't it? There we go. Now we're done. Questions, comments, concerns? Can't do if it's not necessary. I don't know if that is answering your question. You're asking, is there ever a reason why we can't do a sub first? Well, let's just see, like on this one, there's not really a sub that you would want to make first here, because there's not a whole lot you could choose. You could choose x, but we said we don't choose x, so the only thing that would be left would be 2x. But you really wouldn't gain a lot from that. This particular example was an example where if you try to go without a substitution, it just gets uglier. Now, this could still be done. Let's see, how close? Well, we weren't really close to the answer, were we? X e to the root x. Do we even have that anywhere here? No, we don't. So we probably would have been in some trouble up there. Like we would have had some difficulty. Where we got stuck here, where we stopped, this is correct, okay? This is not wrong. It's just what the heck is this? That's the problem. Does that address your question? Okay. All right, let's see what's next on our agenda here. That's an example of making a sub first. How about this one? Creating a reduction formula. Let me come back to F. F's one of the harder problems we're going to do today. So let me come back to F. Let me give you another example. This is an example, you know how you have your formula sheet that has the different integrals on it already, right? That you're allowed to use on certain tests and stuff. Do you have an integral on your, do you have a formula on your sheet for the antiderivative of the natural log of u? You have a formula for the derivative of natural log, right? Derivative of natural log of u is 1 over u. The antiderivative of 1 over u is natural log u. But what's the antiderivative of the natural log u? That's the derivative of natural log, u prime over u. So there's no formula up there? Okay. Well, let's see if we can make one. All right. So if I ask you to integrate this, what seems like the only technique you could possibly throw at this? By parts. Okay, if you're going to do parts, you got to choose one to be, well, we can't use u. How about you want to use w over here and dv, we'll stick with that. What's your only candidate really for w? The natural log u. Does that make sense that that's the only natural candidate here? And that means that your dv has to be du. Now let's think before we do it. What are we going to get when we come down here? 1 over u. What are we going to get when we come up here? U. So we have 1 over u and u. When they come together, it's going to leave you with a 1, right? We should be able to handle that. So dw is 1 over u, and v is u, du over here. dw is 1 over u du. That's the derivative of natural log. The antiderivative of 1, or du, is u. And so this integral up here becomes ultraviolet, but it's not really ultraviolet, right? What would it be? Violet minus, I can't do it. You know what the hell I'm talking about. It's these two multiplied, right, minus the integral of these two multiplied. See, we don't have a cute little saying for it if we're not using u and v anymore. So these two multiplied are what? U ln u minus integral. These two multiplied is just du, or 1 du, isn't it? What's the antiderivative of 1 with respect to u? U. So you get u ln u minus u plus a constant. I saw some squinting eyes when I looked up last time. Do we have questions? You're just fine? Oh, blind. Maybe I'll throw a 1 in here so you realize the antiderivative of 1 is just u. The 1 comes from these two. Check it for yourself if you want. Take the derivative here. Right, you'd have to do product rule on this first one. I always like to do it because it's kind of cool. Let me do product rule. I'm taking the derivative to verify the answer is natural log u. The derivative of this product is the derivative of the first one times the second one, plus the derivative of the second one times the first one. And then you have minus, what's the derivative of u? 1. So you get natural log u plus these are 1, and then you have minus 1, and that's just natural log u. So you can confirm by taking the derivative here that you get the integrand here, so that is the antiderivative. So you are allowed to write this formula down on your formula sheet. I'm okay with you putting this one down there. The antiderivative of natural log of u is u ln u minus u. It does come up sometimes that you need the antiderivative of natural log of u, so just remember the formula for it comes from the integration by parts. Questions? All right. I'm going to try to introduce this idea of reduction formulas. Reduction formulas are formulas that we have for integrals that help us solve very complicated ones. Let me write down what I'm talking about. I want us to show right now that the integral of x natural log x to the n dx is equal to 1/2 x squared natural log x to the n minus 1/2 n integral x natural log x to the n minus 1 dx. Take a moment to jot that down. And I'll put here for n greater than or equal to 1. So why do we call this a reduction formula? Why do you think we call it a reduction formula? Yeah, good. The original integral, right, had x and then the quantity natural log x raised to the nth power. We're trying to figure out what the antiderivative of that was. And what we come up with is a new expression that has a new integral, and that new integral is exactly the same as this one with the exception that the power has been reduced, right? Reduction, by 1 power. So let's say that this was x natural log x to the 3rd power. This new integral, or this new expression, this new integral would have what? 2nd power. And how would I do that integral? I would use this formula again and reduce that 2nd power down to the 1st power. You see? And if this was n to the 80th power, then I would reduce it to 79th, and then that integral would have a new expression with 78th, and then that one would have a new one with 77th, and so on all the way down. It would be a tremendous integral, right? It would be a tremendous expression, but you could do it just by reducing, not doing any integration at all. We're gonna do an example where I'm going to replace this with a 3, and you'll see how it works. But first, let's show this formula is true, right? We have to show the formula works. So here's how we'll do it. First, we start with what we're trying to integrate. And I hope that you can see by the formula we're trying to get to that this looks like a whole lot like integration by parts, doesn't it? You have like maybe this is our ultraviolet and maybe this is our minus integral voodoo, right? So it might be worth it for us to throw integration by parts at this. If we do so, we need to choose a U, we need to choose a dV. Okay. What would you normally want to choose as your U here? The x, because we know in the new integral it becomes a 1. However, if you do that, you're going to have to integrate what? The natural log of x to the nth power. That does not look like a nice integral, does it? It does look like, or it does not? Yeah, it doesn't. It could possibly be done, but it doesn't look like something I want to do. So maybe we switch it up. Maybe we make the u the natural log of x to the nth power, and then we make the dv the x. Try it, see what happens. Let's work with that u first. What's the derivative of u? So what's the derivative of something to the nth power? N comes out in front, right? Natural log x to the n minus 1, right? Times the derivative of what's inside. So what's the derivative of the natural log? 1 over x and then dx, right? Y'all agree that this is the chain rule applied to natural log x raised to the n. N comes out, subtract 1 from the power, derivative of what's inside, dx. What's the antiderivative of x? 1/2 x squared, right? 1/2 x squared. So according to integration by parts, it should be ultraviolet. So 1/2 x squared times natural log x to the nth power minus integral voodoo. So here's my voodoo right here. What happens? How about constants? What do we have? 1/2, right? 1/2. Isn't this n right here a constant? Yes, so I can pull out a 1/2 n. What's still in the integral is what? The x squared, but then that x squared is going to be divided by x, right? So that would be just an x. And then we still have the natural log x to what power, though? N minus 1 dx. And isn't that exactly what I was trying to show? Isn't that exactly the reduction formula here? Yes? So I've shown it's true. Questions? So now let's use it. Find integral x natural log x to the third power dx. And we are allowed to use the reduction formula. So according to the reduction formula here, what's the n that we have for this problem? N is 3, right? N is 3? Okay, so let's write this down. This is equal to, according to my formula, which you have on the previous page, it's 1/2 x squared natural log x to the third. Then what? Minus 1/2 times 3, so 3/2 integral x natural log x to the second, right? 2 minus, or 3 minus 1 dx. That's what we've got. That's just directly plugging into the formula, replacing n with 3, right? Now, this integral is a new integral. It has the same format, so the n for us here is what? Is 2. So we reapply the formula to just that integral, and the power will come down again. But we still have to keep all this crap in the front with it. So we've got 1/2 x squared natural log x to the third minus 3/2. What do you think I should put here after the 3/2? Maybe a bracket or something? And now we're doing reduction formula on just this, with n being 2 now. So that should be, according to the reduction formula, what? 1/2 x squared natural log x to the second, because n is 2, minus half of this is the formula right here, minus half of 2, which will be 1, so I'm going to leave it 1. So 1, I'll put it here, 1, integral what? X natural log x to the first power, right? So just that. And now, I'm going to look at this integral. Now that integral, I cannot use the formula on. Why? Because the power, right? The power, this formula, well, wait, was the formula good? What was the formula good for? Greater than or equal to 1. So it will work for equal to 1. So we can do it one more time, can't we? So that blue part, so I'm going to just keep bringing everything along here. 1/2 x squared natural log x to the third minus 3/2. I'll distribute and do all that in just a second. 1/2 x squared natural log x to the second minus, now this integral is a new bracket. That one becomes 1/2 x squared natural log x to the what? To the 1 minus 1/2 integral x times natural log x to the 0, which is just anything to the 0 is 1. Close my bracket, close my bracket. So isn't this last integral really just the integral of x, which is 1/2 x squared? But then times that 1/2. So, all right, I think I'm almost ready. 1/2 x squared natural log x to the third minus 3/2 bracket 1/2 x squared natural log x to the second minus bracket 1/2 x squared natural log x minus 1/4 x squared, close, close. So just keep in mind here that this whole thing right here turned into just this, right? This right here, antiderivative of x was 1/2 x squared, but then you hit it with this, it becomes negative 1/4 x squared. Agree, agree? The c, I'm going to throw the c on at the very end. So this, we could have thrown the c in right here. We're just going to remember, I don't care about my constant. We'll just tack it on at the end. Now, to do this properly, we've got to distribute everything through and clean it all up. But I'm not going to. I'll just tell you what you should get. When you're done, it's 1/2 x squared natural log x cubed minus 3/4 x squared natural log x squared plus 3/4 x squared natural log x minus 3/8 x squared plus c. Now, you do have some things in common here, like you have all terms have x squared, so you could factor an x squared out, and you could factor fraction out too, but good enough. What did we not have to do at all in this problem? We didn't have to integrate at all, did we? I mean, well, wait, hold on. We did integrate x, didn't we? We did integrate x. But other than that, the reduction formula allowed us to totally go around having to use any integration by parts at all. But we had to know the formula existed. Questions? Integration by parts? You could have done that also, yes. That's what I almost did, but the formula still applied, so I did it I just used it one more time. Is that on your formula sheet? It's not on there. You don't need it. That brings me to my next question, was what reduction formulas are on your sheet? Are there any on there? On your cheat sheet? I know the back of the book has them, but I don't know if yours does. Does anyone see any? No? Nope. So there aren't any on your formula sheets, but there are some if you look, if you have a book that has them. Well, maybe there aren't. Oh, yes, there are. There's another, okay, I have formulas up to 29, right? On what you can have on the test. I have up to 29. Your book actually has, on the reference pages, they actually have formulas that go all the way up to 120. And when you get to reference page 7, if your book even has it still, no, it's not page 7. It's on reference page 9. There's some reduction formulas in here. But there's no sense in having a book full of integral formulas because if you wanted to look for integral formulas, you could find a book as big as this book full of formulas. Like, there are lots of formulas you could generate for integrals. But who wants to sit there and flip through a 500-page book of integral formulas looking for the specific integral you have? The only thing I'll ever ask you to do for reduction formula would be to show this reduction formula is true. Like, show it. All right? I guess what I'm getting at is they're useful, but they're not going to come up all the time. All right, do we need to get up and do some jumping jacks, or should we just do a quiz? What do you think would wake y'all up and get y'all blood going before we finish up in here? Jumping jacks? You prefer jumping jacks over a quiz. How about we do a group quiz? Sound better? All right, let's do that. So I'd like, you can work together. Let's try and have, like, I guess everyone at the table can talk. And, well, how about I give y'all 3 different problems? Yeah, we can do that. We can do 1, 2, 3 different problems, and let's just see where y'all go with them, all right? All right. So we'll call this, and guys, y'all are going to have to join in somewhere over. We'll call this table 1, and then 2, and then 3. And I'll give them, you know, easy, medium, hard. Does that sound fair? No. What I'm going to do is I'm going to go to the chapter 6 review and pick a couple of problems out of the review and see how they look. Well, better stay away from that. Hold on a second. I think I did that one. I did. All right. go for it. Table 1, Table 2, Table 3. If your table finishes, then start working on the other ones that the other tables are working on. But I want every table to come to a consensus, like we all agree this is the answer. So just so everyone knows, what we're going to do is these 3 problems, all 3 to be turned in next class, beginning of class, I'll count it as a quiz grade. Okay? So you can take it home and finish it off. And then the homework assignment for all 3. Okay? So make sure you write them down before you go. And that way you can take them home and make sure you really, do them nice and neat on a sheet of paper. And don't be like, hey, it's stuck in my notes here. Can I just turn in my notes? Just dedicate a sheet of paper to the assignment. And then these are the homework problems. Next class, we move into the new technique of integration, all right? That's going to be it for today. So I'm going to stop the video. Just continue to work, or you can pack up. I'll let you go a little early today if you want to. Everyone understand what's required for next class, though? All 3 turned in on a nice, clean sheet of paper. And then do your homework.